Welcome to the GoEngineer YouTube channel. Before we get started, make sure you hit that subscribe button if you haven't done so already. All right, we'll go ahead and get started here. For those of you in attendance, thank you for your time and for joining us here today. Today's topic will be our deep dive with CFD with SOLIDWORKS Flow Simulation. My name is Enrique Garcia, and I'm an applications engineer here at GoEngineer. I specialize in our simulation products. Today we're going to be introducing SOLIDWORKS Flow Simulation, as well as giving you a good overview of the product and its capabilities. So here's the agenda of topics that we'll be covering today. Also, we're planning on recording and sharing this webinar to everyone on our YouTube channel at some point after our broadcast. So if you couldn't attend the full session here today or something comes up, you'll be able to watch this full presentation at your convenience at a later time. Also, if you have questions during the presentation, feel free to use the presentation UI in the virtual meeting software to post any questions you may have. If everything goes smoothly, I'll be able to see them and, if possible, try to answer them as I go along here as best we can. We'll also have some dedicated time after the presentation to answer any related questions as well. All right, so with that being said, let's jump right into it. So let's begin by introducing SOLIDWORKS Flow Simulation. Since you're here, you're probably a bit familiar with what the tool does, or at least in general. For those of you that are coming in completely cold, flow simulation is meant to simulate different types of fluid mediums in and around your products. It's fully integrated into the SOLIDWORKS ecosystem, offering some good benefits like revisioning your model and then rerunning the flow project right afterward. So there's no need to export, then import and readjust or reset up your model in different software. Or another thing to mention here on this slide is that the main meal ticket for the software is that it can simulate fluid mechanics and heat transfer very, very well. In addition, there are other tools in the software that allow flow simulation to keep its strength for many other applications. Let me touch on some of the more noteworthy bits from this slide. Among these capabilities, some that I like to point out here are internal and external flows. You'll be able to simulate fluid interaction within pipes and valves or pumps, as well as investigate the aerodynamics of your designs by influencing the environment around the exterior of the designs, like in a wind tunnel situation. Also, as mentioned in the previous slide here, we're able to model heat transfer. So all three mechanisms of heat transfer can be considered: conduction, convection, and radiation. In addition, forced or natural convection models are also available. Oh, and with using the time-dependent capability here, you're able to calculate the response of heat energy in fluid mediums as a function of time. For example, we can see temperatures and how they develop as a function of time, and when different components see the highest temperatures during a heat loading cycle, for example. Also, with the rotating components capability here, we can simulate and analyze pumps or impeller designs by assessing the rotation of our fluid mediums in and around designated rotating geometries. With the results exchange capability, this ability is to be able to export flow simulation, thermal, and pressure results out of flow simulation, and then import it into our native finite element analysis tool, SOLIDWORKS Simulation. We can then post-process results in that tool, and we can obtain things like stresses, displacements, and strains due to the response of the model. So everything on the left of this slide here is what comes in and is included with what we call SOLIDWORKS Flow Simulation Standard. In addition to these capabilities, we have two additional modules that can provide you with some specialized setup capabilities based on specific industries. These are the electronics cooling module and the HVAC module. For example, the electronics cooling module, this gives us additional materials for chips and other specialized aspects or materials of the model. It also gives us the ability to set up custom PCBs, allowing for specific layer definitions and processor or generic chip heat sources using the two resistor model, and also specializing or specialized heat pipe setup capabilities with the heat pipes definition tool. For the HVAC module, this gives us additional specialized materials and additional radiation capabilities for setups with regards to HVAC. This module also gives us specialized post-processing plots and capabilities that are required by the heating, ventilation, and air conditioning industry. So again, this is a very general overview of the capabilities and modules that are available with SOLIDWORKS Flow Simulation. So now that we have a good foundational sense of what the tool can do, let's introduce the basic setup and workflow. For this, we'll be using this partial model of an exhaust system where the exhaust from a motor and the air meet in the system. So let's open up SOLIDWORKS here and we'll review the setup for this particular model. All right, so here's the first model. Again, it's the exhaust. We're going to be looking at the way the exhaust enters this little darker portion of the piping, and then air is going to be introduced into this section, and then this area is going to be where the air and exhaust leave the system. The first thing I like to do is I like to make sure that the flow simulation add-on is turned on. So we'll go in and look at that here first. So this is going to be a line item in the list. As long as you have the license active and installed, you're going to be able to see the flow simulation line item. I have it turned on for this session and also for startups. In case I close and then reopen SOLIDWORKS, I'll have flow simulation turned on as well. And so let's start by doing a setup here. This gives us two things when we have the add-ons turned on. It gives us our flow simulation tab, and it also gives us a dedicated line item under the tools menu for flow simulation. This is how we can potentially set up different aspects of the design, or we can do it from the flow simulation tab in that command manager. To start a new project, there's two ways. We can go in and do it with what we call a template, just like how you start the SOLIDWORKS model when you go to File, New, and you can click on the different templates that are available. You can do that with Flow Simulation by clicking on New, and then you can pick a different template here, assuming you have different templates set up. Now, most of us, including our most advanced users for flow simulation, we prefer to run through and set up our flow projects using the wizard. This gives us an ability to efficiently go through all of our initial conditions with the wizard and then set up the very specific or localized regions with our different conditions. So let's go in. I'm going to use the wizard tool here for all of my products and examples here. And so we can give this thing a project name if we wished. We can see that the projects are configuration specific. So if you have a certain combination or geometry for a configuration, make sure that's specified here under the configuration section. We'll click next. I can specify different units, perhaps under temperature. I can pick maybe Celsius or Fahrenheit, whatever you're more comfortable with if we're looking at temperatures or different rates for different things. We have all these different categories for all the different units you can choose from and specify. I'm just going to click next here for this. Next, we have our analysis type section. So this is a portion of the wizard where we can specify between an internal and an external analysis type. Now, if you care about the model of fluid geometry or fluid medium inside of an object, for our particular exhaust system, and nothing else, we're going to be picking an internal analysis. If you're doing pumps or pipe systems, things that are fully enclosed, we're going to specify the internal analysis type. If you cared about the exterior fluid medium surrounding an object, if you're doing like a heat rising or natural air convection studies, and you have heat involved and you want to see what happens with that system, then it's probably a better idea to choose an external analysis. This will give you the ability to analyze the fluid flow on the exterior and the interior as well if you have openings in your product. For us, we're going to keep this on the smaller side and looking on the interior structures and volumes of this. So we're choosing internal. Also, a quick note, when you're doing an internal analysis, you can see my model has already done this, but we have lids plugging up all of the different outlets to my system. So that's going to be a requirement. Whenever you're doing an internal analysis, you want it to be airtight. So down below, we have something called physical features, and these are different models and capabilities we can turn on that will help increase the accuracy of our projects. For us, we definitely want fluid flow turned on. We want to model the fluid flow of our object surrounding our different geometries of the object here. We have conduction, which we'll do shortly in the next example, where we can map out our heat energy and we can see how our heat energy travels through and develops within our structures and our model. We have our time-dependent tab or checkbox, and this allows us to be able to do a transient study and see how our different fluid mediums and temperatures and variables change as a function of time. We also have gravity. Now, if you have heat, I keep going back to heat, but if you have heat an example with heat energy, different fluid medium maybe changes, the density of it could change depending on the heat aspect. You're going to be able to want gravity turned on so you can have heat rising and have that natural convection behavior being captured in the calculation. So if you ever need gravity for any reason, that's just one example, but if you need gravity for something related to how it affects your fluids, definitely have gravity checkbox turned on. In this case, we're going to be having a lot of just fluid medium moving through the system very quickly. We don't need necessarily gravity for this. We also have rotation. The rotation checkbox allows us to go in and assign different regions of the model to see how fluid flow will be able to rotate around structures, especially blades maybe for propellers as a quick example to give you there. We also have free surface. Free surface allows you to be able to take two immiscible fluids and have a barrier or a boundary between the two to see how they interact with each other. Think of vinegar and oil, or think of air and water as examples for how to model the free surface between the two fluids. For us, we're just strictly looking at the fluid mechanics of the structure, so we'll leave fluid flow and then we'll hit next. Under default fluid here, we're going to be expanding and choosing air under gases. We also can add, and this is a part of the engineering database of different items, and in this case, fluid mediums that we can choose. We have our predefined category, but we also can do a user-defined category. For example, here I've gone in and I've made a custom exhaust gas material for our exhaust fluid medium. So I'm going to be adding that to the list as well. I'm going to hit next. We have some initial wall conditions. So if I had heat conduction, I can choose what I can do with the exterior surfaces. Roughness, if you knew the default roughnesses of all the surfaces in general, you can choose this globally here, and you can always choose this value locally if you have specific areas where that changes. But that's just in general here, the wall conditions. Hit next. And lastly, we have our initial conditions. Initial conditions, you can specify initial temperatures, pressures. If you have generic fluid medium velocity rates, then you can specify them here under velocity parameters. We're going to be specifying this locally ourselves a little later in the setup. For us, we do want to go in under concentrations, and initially we want to make sure that we have air being our initial fluid medium throughout the whole system. I'm going to make this as a mass fraction, and I'm going to be entering 1 for air and entering 0 for the exhaust gas. So these are the different areas that we go in and we address when we do the wizard and we do our initial conditions. So I'm going to hit finish. And now for the next phase of this setup is going to be applying the locally applied conditions. We're going to be putting in, when it comes to these internal analyses, we need to specify where our fluid medium enters the system. In this case, we have air entering this particular lid, and then we're going to be entering an exhaust gas coming into that side of that lid. And then we want to specify outlet conditions. In this case, we will have an outlet on this particular lid. So this will be a combination of our air and our exhaust gas leaving the system. So let's do that next. We're going to be doing this with using this particular folder called boundary conditions. So I'm going to go in and apply my first boundary condition. Let's do the air here first. So I'm going to go in and pick my internal face there of this lid here. I'm going to be picking this particular inner wetted surface of the lid there. And then I want to go in and choose, and again, depending on what data you have, in this case, I have a inlet, I have a mass flow that I want to enter. So I'll be specifying an inlet mass flow. Here's where I'm going to be putting in my magnitude value. I'm going to be putting in 0.05 kilograms per second. Down below, we have other conditions that we can specify at the inlet boundary there for this particular model. For us, the one thing that I want to specify is going to be my concentration. So I want to make sure that air is the only thing that comes in. So again, I want to leave this as mass fraction, and I want to make sure that air is set to 1 and my exhaust gas is set to 0. Let me click OK to accept that. That's my first locally applied boundary condition. Now I want to do something similar with the exhaust gas inlet. So I want to go in and rotate my model, and I want to pick something similar here for the exhaust gas inlet. Once again, I'll go into the boundary conditions and I'll choose Insert Boundary Condition. I want to specify that inlet surface there. So I want to use maybe the Select Other tool. So maybe choose that inside surface there. And again, for the inlet mass flow, I'm going to be entering a value here. That's going to be 0.009 kilograms per second. And like before, I'm going to jump down here to my surface concentrations. And this time I want to make the air 0. And I want the exhaust gas to be set to 1. So again, 100% fluid medium is going to be the exhaust gas coming in through that boundary. I'll click OK when I'm ready on that. Now I'm going to specify the outlet condition here. Let me put this into, I'll just rotate the model around. And now to specify the outlet, I'm going to do, again, one more thing. Under boundary conditions, I'll do a right click, say Insert Boundary Condition. And again, we're picking the inside lids. I want to use the Select Other tool. You can also do other things. You can select, let me choose that particular face. You can also do the actual section tool with SolidWorks as well. If you want to section a model, and get it to a point where you can see the inside surfaces and pick them easily. Or you can go to the SolidWorks options and you can make sure that you select selection on transparency, an option that's available there, so you can more easily pick the inside surfaces of things. That's all fair game when you're doing selection with flow simulation. So here for this, because this is not an inlet, we're going to switch the type here down below from flow openings over to pressure openings. And we're going to specify the surface there that's going to be open to the environment. This is going to give me a relief point for my fluid to exit the system. So for this, we'll leave everything else at default, and we'll click OK. So that's going to be the setup when it comes to an internal analysis. This is the basic setup and workflow when doing any flow simulation project. The last thing we want to specify is something called engineering goals. So engineering goals are a way we can tell the software what we care about results-wise in our calculations. You can do engineering goals in a couple of different ways. If I do a right click here, you can see I can insert and ask about a global goal. Maybe you can do pressures, we can do velocities. Any result that can be set globally with the entire volume of the model is going to be set as a global goal here. We have also point goals. So if you have specific points or vertices in the model or locations in 3D space that you cared about results for, you can specify that as a point goal. You can do a surface goal. Again, if you have a surface in mind that you care about, you want to get maybe a temperature for, or maybe a pressure on a surface, something that's maybe sensitive to a pressure that you need, you can specify that. Or a volume goal. If you have maybe a reference body inside of a fluid cavity that you cared about knowing what the velocity was across like a certain boundary of a sort, you can do that as a volume goal. And you have the equation goal. With the equation goal, you can go in and specify an expression, and you can enter and create an actual equation for something to give you a reading when you're going in and looking at results. So again, these are all things that you're wanting to maybe formally ask the flow simulation software to calculate, so that we can have proper convergence and maturity of the results, so you can have assurance that you have results that are as accurate as possible with the flow simulation tool. For us, let's do a couple here together. Let's do a global goal here first. So again, a global goal will just give us a value for anything under this parameters list that will be the entire volume of the calculated volume of the project here. For us, let's just look at maybe the maximum velocity. Let's just choose the maximum column there. And again, this is going to go in, and when it's doing its calculation, we'll converge results for the maximum velocity for the entire volume of this project. Let's click OK. That's my first goal that I want to keep track of. Let's do some surface goals here as well. So the first one I want to do is maybe let's look at the outlet faces here, the first. So maybe I want to do a mass fraction of the air and a mass fraction of the exhaust. I want to see what combination of those two fluid mediums occur at the boundary there of the exit of the system. So I'll do a right click on goals, and I'll say insert surface goal, or you know what, I could also maybe even pre-select For example, I can go in and choose the environment pressure condition, so I can pre-select the surface for that, and then I can do a right click on the goals and say insert surface goals, so I don't have to use any of the SOLIDWORKS selection tools again. And then I can go in and choose, let's say, the mass fraction here. Let's say mass fraction of the air, and we'll do an average. And while we're in here, we'll do the mass fraction of the gas exhaust as well. So this will give us a total of two goals, two surface goals for both of those items. So that's going to be for our outlets. Let's do some for the inlets here next. So maybe we'll do one for the air here first. So maybe I'll select the reference to highlight the inside surface there for the air of the lid. And then we'll go to goals and we'll say insert surface goals. And for this, since we know the mass fraction of those already, how about we look at maybe pressures. We'll do like a static pressure. We'll do an average static pressure for that. And we'll also do an average static pressure for the exhaust. Again, we're picking items that we want to make sure that we get results for. This way, when we run the calculation, we can converge our calculation results for these specific values. This will give us the best chance for accuracy when we look at these results. So that's the whole setup for this particular model. At this point, let's go ahead and if we were to run this, we could hit the run button, we get some information to start a new calculation, and we can run this particular design. Now, instead of running through the whole thing, let me cancel this. This takes about 4 to 5 minutes to actually run. So instead of running the actual project, let's go ahead and open up a project that's already been completed so we can step through the different results. So let me come in and jump and activate an already completed project. And once we have that activated, let's go ahead and load those results. I'm going to come down and load those here with us. And let's take a look at some of the more popular results that we can do when we're post-processing results in flow simulation. The first plot type I want to look at is a cut plot. So a cut plot, if I go in and I do an insert, let me just show the one that we have here, and we can edit one together. And all it is you're picking a reference of some sort. It can be a face, it can be a plane, and we can offset that as much as we'd like. In this case, maybe I'm offsetting it kind of down the middle of the main pipe or tube there of the exhaust system. I can specify under contours what I'd like to display, in this case a velocity. I can also display vectors or streamlines. I can hit the preview button to start to display what happens with my results. So I can see some information on that. I can click OK and I can start to interrogate my results using these cut plots. Here's another cut plot that I've made on the other side of the model on the surface here. Here I've made a what we call a 3D cut plot, where I can see in this case it's the mass fraction of exhaust, and we can see that the plot lifts from the reference surface the higher the magnitude is. In this case, the mass fraction of exhaust gas, and as it goes to 0, it goes back to the surface there of the cut plot reference. So just another way to visualize different results, in this case with cut plots. Another way we can visualize maybe on the surfaces of the models is with a surface plot. In this case, if I show a surface, I can look at, since we're looking at the exhaust or the mass fraction of exhaust, I can confirm that I'm getting 100% exhaust entering through the exhaust section of the system and 0 from the air side. And I can see, again, we're modeling on the surfaces in this case, so we can see how my exhaust gas starts to mix with the air fluid medium, and then it starts to mix a lot more, and the concentration drops as I go further and further away from the mixture point. We can also see here I have an outlet. For the outlet profile, I can see what that mass fraction of exhaust is, which is about roughly 50%, or between 40 and 50% here on that surface there concentration. So those are some different things you can do with plots, in this case surface plots. Something else that's quite popular is a tool called flow trajectories, which allows you to visualize or characterize your fluid mediums with any kind of concentration, in this case, maybe of the exhaust gas or velocities, pressure distributions through the fluid mediums themselves. So here's an example. If I go in and I can take a look at this first exhaust side here of the model, I can choose that inner surface, and then I can go in and specify what I want. In this case, I want to inject 20 units or points into that surface, and I want to map them and have it develop through the geometry based off of the fluid trajectories and fluid flow of the model. In this case, I can also specify how I want to display these in the form, in this case, maybe of arrows. I can pick a size, maybe 1 millimeter arrow sizes, and I want to look at the mass fraction of exhaust gas. So if I click OK, I can start to develop that, and I can characterize that using my flow fields of what that will look like. And what's nice about this is in a presentation, I can display and play and get a very good animation of the exhaust gas traveling through the system. Now also we can complement with other flow trajectories. We can do these separately like you see here. We have an air side. This time instead of using arrows, we're using pipes instead. So we can have a nice little static side. So we can see how, in this case, they're both mass fraction of exhaust gas. In this case, this is air, right? So this is going to be a 0%, and then as it goes through the mixture point, it increases to about 40%-ish, and then it exits the system. So again, just different ways that we can show our results here. Let me hide those. If you want to get very specific with your results, you can go in and do a surface or volume parameter or a point parameter value, which means I can take other areas of the model that I care about and I can maybe call them out or probe these areas for information to get some quantitative results. For example, of maybe a surface parameter here. If I want that surface, we know we had that as a goal, but if I had another surface of interest, maybe on the side of the inside of the tube, I can right-click parameters. Let me edit that one here with you. And I can pick a surface, in this case, that surface, and then pick any one of these parameters in this extensive list. So I can then call out and show that so I can get the information of what that is here. So on average, I'm about 18% mass fraction of exhaust gas on that particular surface. So I can call that out there. Also, since we've already set this up in terms of goals, let me hide this one. Since we've done all these goals on the top here of our setup of our model, I can actually call those out here under our goals plot. So I can do a right click and I can say insert, and that's what I've done here. I can edit that particular goal plot and I can pick different things. In this case, maybe the mass fraction of exhaust gas, that same one we did as a surface parameter. I can go and show that here more formally, or I can pick them all, right? I can go in and pick all of those to show, hit the show button, and I can call all of those out and get information for all these different aspects of my results. So this is the basic setup and workflow that you can expect when doing a flow simulation project. The next type of example that I want to review here with you is how to set up a thermal analysis. For this example, we'll use this generic electronics box with some heat sources on the various components. We'll also have some fans to help force the air into the electronics box for cooling. So although the setup here is for electronics, it can easily be applied to any thermal application. All right, let's go on back to SOLIDWORKS for this here. Let's close that and open up the next model here. So when you're doing a thermal analysis, you'll have to set up a couple of additional items, that being the solid materials. You want to go in and specify all of your materials for all the different components. And you want to specify your heat sources. Now that can be done very generically, like what we'll be showing, but it can also be done if you have maybe one of the other modules, like the HVAC module, or in this case, the electronics cooling module, can be done with some more sophisticated or specific applications. So we'll be showing you a little bit of both for this particular example. Now, flow simulation can take a bit to run, so here we have an already completed set of projects that we'll be reviewing in a bit. But first I want to show you some of the setup items first. So let's start by going in and going through the wizard, and let's show you what would happen when we start a new project from scratch, and how we can specify thermal analysis. So I'll go over to the wizard, And using the wizard, I can give it a name, maybe thermal analysis, something like that. Click Next. Enter our different units. In this case, probably temperature. I want to change that to something, maybe Celsius. Hit Next. Under our analysis type, this is going to be an internal analysis. We have the entire model airtight with lids for all the different ventilation ports. So that's all been taken care of. And for us, it's important that we want to have conduction turned on. So we're going to make sure that conduction is turned on. This is going to give us the ability to have our heat transfer through conduction on. Now for convection, convection is automatically assumed. We're going to be doing some fans to have some forced convection happen, we're not going to worry about natural convection. So we don't need gravity turned on. Maybe in the future, I want to rerun this just to make sure there's no significant changes in the results. That can be something that can be done. But for now, we're just going to have the conduction mechanism of heat transfer active, and we'll hit Next. For our default fluid here, it's going to be air. So I'm going to expand gases and choose our air default fluid, hit Next. And now because we have conduction on, we need to specify what our default solid or default assigned solid will be. In this case, since we were going to be going through and assigning every single component, the one thing that we're going to be not assigning specifically is going to be some of the ICs. So I want to go in under IC packages and then maybe just leave all the typical chip array as the default solid. Everything else is going to be assigned manually here later on. So we'll click Next. Under wall conditions, we'll just leave all the default wall conditions and the default initial conditions as they are. So normally I would hit Finish, and then I would go in and assign all of the local conditions to for all of the heat sources and all of the solid materials. But for now, we've done all of this here, so we can review that here next. So I'm going to hit Cancel for now. And then I'm going to focus the rest of our setup on this already completed external fans project. So again, there are a couple of major differences here with a thermal analysis. The first one is going to be the fact that we're going to be assigning solid materials to the model. In this case, to assign solid materials, very, very straightforward. You would do a right click, and you can either say Insert Solid Material to do them one batch at a time, or if you've already set up materials in the SOLIDWORKS CAD model, and there's an equivalent material in the SOLIDWORKS Flow Simulation database, then you can choose Import Data from Model to help save you this extra step. For us, we've done this as the Insert Solid Material, and we've assigned all of these different materials to the model. If I go into one just to take a look at how it looks for this, you're basically picking the individual components either from the graphics area, or you can pick them from the SOLIDWORKS design tree, and then you're specifying the material here from the engineering database. You click OK. Again, pretty straightforward when assigning your materials. The next thing that you're going to do, or the next major thing that's going to be done with a thermal analysis, is you want to assign how you're going to introduce your heat energy to the system. Now, there's a very generic way to do that and some very specific ways. The more general way of doing that is by using heat sources. So you just do a right click and you say Insert Surface Source, or you can say Insert Volume Source. And we've done a couple of volume sources here. For example, we have these components there. If I edit that, we can see I've chosen those 4 instances of the component, and then I've entered a total heat generation rate. Now again, all 4 of these components are going to generate a total of 2 watts for all 4 instances. You can, upon the initial creation of these, you can specify per instance. So I could maybe do a total of 8 watts. If I did 2 watts per instance, so you can specify upon the creation of this whether you want a total or a per item kind of initiation or initial assignment of your heat energy. So that's how we've gone in, and it takes some time. You need to go in. We did them for these ICs as well. The capacitors we did them as in the form of a temperature. Again, we just specify those 4 capacitors, and then under parameters we chose the temperature, and then we enter the temperature. So that's just some general ways you can introduce heat energy. A more specific way that you can do it, and this is, again, if you have some of the more advanced capabilities from the modules, like the HVAC module, or in this case, the electronics cooling module, you can do what we call a 2 resistor component definition, where again, if you have, in this case, the main CPU, we have the geometry for it. I can specify the case surface for the model, the top surface, and then I can specify the component, or in this case, the two components that make up the main CPU. And then under component, with the electronics cooling module, you have a pretty extensive list of the different components that you can specify for the two resistor component. And then you enter your source and your general temperature for the initial solid temperature of the IC. So again, this is a very specific way of modeling a very complex geometry with a mathematical model with SOLIDWORKS Flow Simulation to help save computational time. Otherwise, if you're going to be modeling all that geometry of the IC and you're wanting to get a very accurate heat generation from this, that could be computationally very expensive. So this, again, these models help simplify without losing accuracy on these specific areas. So that's really what's involved when you're doing thermal analysis. The last thing I want to show is when you're doing fans, that we're going to be forcing air fluid through the system. And here's an example of a fan here. I want to just edit here with you. There's three ways we can apply fans. In this case, if we have a fan that's sitting on the outside of the structure as an external inlet fan, we then specify the surface that's going to be introducing the fluid flow into the system. And then under the fans database here, we can specify some generic fans, or if you have the electronics cooling module, you can be very specific. And we have a very extensive list of the more common fans that are used out in industry. In this case, the PAPS 412 axial fan that we can choose. If you don't have the electronics cooling module or have just the standard flow package, and you wanted to put in a specific fan, that's fair game. You can do that. I can click on this Create/Edit button, which will open up the engineering database, and I can create my own fan. I can go in under User Defined and enter my own fan, and I can enter specific properties for that. For example, maybe I want to redo this 412 fan. I can go into the item properties under the User Defined section, and I can make a new item and enter these values. And if you have the white sheet from the fan curve from the white sheet, I can enter that as well here as a volume flow rate pressure difference value as a function of the volume flow rate. So again, you can enter these things manually and without having the electronics cooling package specifically. And that's how we did the other remaining fans. So some other aspects of setup here is going to be the goals. If I scroll down here, we have some of the engineering goals. We have a global temperature of the fluid medium of the whole volume of the model. We have some flow rates for the surface goals, for the inlet surface goals. And then we have all these temperature, these volume goals for all of the main components of interest. And that's one of the main things when you're doing electronics cooling. You want to make sure that your certain components that are sensitive to temperatures don't go above a certain temperature cutoff. Otherwise, something could happen to the component, right? So we have some operating limits for temperatures, and we want to make sure we satisfy them. This is a great playground for exploration for these responses for these temperatures. So at this point, you would run the study. In this case, this one takes about I think it's about 12 to 15 minutes to run this particular project, but we have pre-run, and let's load the results just to take a quick peek at those results. Now, interrogating thermal studies and thermal analysis is just the same as we explored earlier with the basic setup and the exhaust system we saw earlier, but we have our cut plots here. I can show those, and we can look at what my fluid flow temperatures look like close to the different components. Let me hide those. We can do surface plots like we did earlier, and we can see what those surface temperatures are at the individual components as well. So here's some of the temperatures for the PCB. And we can see the most of the heat energy is happening at these chips here on the very top of the PCB, and that PCB is heating up quite a bit. We have flow trajectories. In this case, this flow trajectory is showing the velocity of our three fans and how that behaves and how it's reacting to the different components. Here we can see a bit of some recirculation in that area. We can maybe go back and change where components are put on the PCB to help maximize the way fluid flow travels through to help cool the different components more efficiently. And then we can look at our goals plot. Again, our goals plot, if I look at that, we basically had a couple of, we had one global goal, we had some volume flow rates for the different fluid flows, but then the ones we really care about are going to be our temperature, volume temperature goals for the individual components that are sensitive. Then I can click the show button and I can get a definitive value for what those temperatures were for these individual components. And so that's what working with thermal analysis looks like with flow simulation. The last example that I've prepared here for us today will show you how to use parametric studies to automate the exploration of designs and flow projects so that you can change different variables and see the response of our fluid flow with the model or project changes. So in this way, we can explore different trends and limits to our designs. For our example here, we'll explore the lift and maybe drag force and the coefficient of lift behavior of this standard airfoil design as we change the angle of attack of the wind hitting the front of the design. When we open up SOLIDWORKS here in a moment, we're going to review the flow project setup and learn how to easily use parametric studies to automate the creation of the different flow calculations so that we can do the change of the airfoil's angle of attack there and sort through the output results for the comparison and looking at trends. And we'll be able to show how we can do some automated graphs for this. So let's go back to SOLIDWORKS one more time here and step through that example. So here's the example of the airfoil. For the setup, what I did is I did a slice of the model just to help with the automation of the model. I could do the whole wing, or I could do maybe a 2D study of the design. I started with a little slice here just to see what would happen if I would get similar trends before I jumped into a full and more accurate setup for this wing analysis. So basically what I did, if I look at my setup here under general settings, this is how I set up an external analysis. And all I would do is if I was in the wizard, I would go in and switch it to external analysis, make sure fluid flow is set so that I can get my fluid flows through the whole system. For my fluids, we're picking our air fluid medium, default wall conditions, and for my initial and ambient conditions, this is where I can specify the cruise speeding or the cruising speed of my air fluid medium. I'm basically doing the wind tunnel setup here, so I need to specify in this case the negative x direction a magnitude here of it looks like 140 miles per hour is what the wind is doing along the negative x direction. So that's how I've set up my external analysis. It's quite straightforward. The only other setup aspect of it is adding my engineering goals. So for my goals, I did a lift goal here. So let me take a look at how we did that. We did it as a surface goal, and we picked the surfaces of the wing, and then we told it to keep track of the force in the y component or the vertical component. We did something similar for the drag force. We went and picked the specific surface, and then we told it to look at the x direction for a drag direction. And lastly, we did a coefficient of lift equation goal. And if I look at that, it's basically, it'll open up the equation editor. We can then pick specific goals to add to our expression list. We can also add initial conditions and other aspects to our setup in our equation expression. We can go in and pick them here from these different icons. I can do another goal, or I can do a simulation parameter, where I can expand and I can pick the different things that I need. For example, this is where I picked my velocity here. So if I change my velocity in my initial condition setup, it'll automatically update the change in my equation goal. Let me cancel out of that. At that point, I went ahead and I ran this just to make sure it ran. And again, this is going to be the model seeing your fluid flow at 0 degrees. And the way I control that pitch of the actual airfoil is with a mate. If I go back to the SOLIDWORKS design tree, I've basically mated the top plane of the airfoil with the top plane of the assembly, and then that can be changed there in the mate. That's basically this angle that I can change, and that's how I'm going to be driving the change to my parametric study, so I can automate the different pitches of the airfoil here in a moment. And I went ahead and ran that just to get some results, and I can look at what those are here just to make sure they're running and it's giving us some initial results. So that looks correct. So let's talk about automating this next. Let me hide those results real quick. And the way you automate with SOLIDWORKS Flow Simulation is by using what we call parametric studies. To start a parametric study, you go up to your Flow Simulation Project Manager section, and I can do a right-click on an existing project there, and I can say New Parametric Study. Now, there are different ways to automate with parametric studies. You can go in and do some goal optimization, or you can do some DOEs as well. For us, we're going to just stick with the what-if analysis so that we can then enter as many variables as we want and then get outputs that we want. For us, I want to go in and enter that dimension variable. So I want to go in and choose add dimension parameter here under this UI. And then for add parameter, I want to go in and double click to activate and show any dimensions that you want to change. In this case, my dimension is driven by that mate, the angle mate. So I'm going to choose my angle mate. That's going to populate that one dimension. I want to click the OK button. That's going to give us my variable that I'm going to be changing for this particular parametric study. Now, how we're going to be changing that variable is going to be under values. I can double click on that values section, and then I can go in and specify how I'm going to be entering these. I can do them manually, range with number, or in this case, maybe a range with step. For the step size, I want to maybe make that 5. So I want to make that 5 degrees, and I want to start at 0, and I want to end up with 70 degrees. So this will give me about 14 or 15 with the initial configuration or the initial project that it'll rerun. So those are my input variables. And again, I can do more variables if I wished. I can do some initial conditions. Maybe if I wanted to vary the I don't know, under general settings, maybe the wind speed, right? I can go in and change the velocity in the x direction. So instead of leaving it the 140 miles an hour, I can also make that a variable and change and see how that's going to affect my performance as well. So I'll skip that for now. I just want the one variable. So those are my inputs. Now let's talk about outputs. For outputs, I'm going to click on the Output Parameters tab, and I'm going to be picking, in this case, my goals. So these are going to be my outputs. I'll just choose all 3 of those goals. I'll click OK, and those will be my outputs. Next, I'll click on the Scenario tab, and then this is going to set up my different iterations or my different instances of combinations. So now at this point, I'm ready to go. I can hit the Run button, and it'll calculate each of these design points one after another. Or if I have a more sophisticated chipset, I can do more than one instance at a time here, depending on what your hardware performance is on your machines. You can increase the speed or the efficiency of running these individual projects and kind of divide and conquer, if you will. For us, I'm going to stop and I'm going to open up the already completed design study, which is going to be down here, this already completed project. And I'm going to go back into the Scenario tab, and this took about 30 to 35 minutes to run every single design point on this particular machine. And this is the data we get. We get the lift, we get the coefficient of lift, and the drag force for as the model is seeing a pitch and a change in the angle of attack of the airfoil. Now I can get information for these. I can click on the individual design points, and I can go in and I can actually create a project for that. This will take the actual data results and it'll make a new project so I can interrogate with individual cut plots and flow trajectories, all of that detail we've seen when post-processing. Earlier projects that you've seen in this presentation can be done by creating a project. Or if we only cared about these particular result values, I can go over to goals. And I can go in and I can plot those. I can change this pull down, this draw view. I can go from table and I can change that and I can look at these as a chart. So this is again as a function of the angle of attack. So we can see that my lift there is increasing as my angle of attack, my pitch changes for that airfoil design, my drag force is dropping, and we're seeing the coefficient of lift also change to a point where it stalls out maybe a little bit here. And again, this is my first pass of this project. I have to go back and look to see if there's anything else I can add as far as friction or surface roughness for the model to make it more accurate. Maybe do a model where I'm running maybe a larger portion of the computational domain. So there's a couple other things I can do to increase the accuracy of this design. But this is a good starting point. We've gone in, we have a starting project, and we're automating the fact that we're changing this angle of attack to get all of these calculations done automatically. I've gone in and I partially set this up. If I were to do this manually, let me just close this out. This is what it would look like if I were to do this manually. And if I go in, I would have to go to every single configuration and make a couple of these configurations and change that angle, that mate angle for each one, and then set up a project for each individual one. It's time consuming. You can clone projects and copy them, but then you'll have to make changes to the items, rerun each individual item. You're going to basically have to babysit them, and then you're going to have to post-process each result, export it into Excel perhaps, and then graph these trends. Versus if you just run this parametric study, you can then hit the run button and go off and do something else, and then come back and look at some trends. So again, the automation is one of the main meal tickets for this type of exploration, and we can do it just fine with flow simulation. So that was the last example I had for the webinar. Before we end with any questions, I just wanted to promote our dedicated GoEngineer YouTube channel. We post videos here very regularly, and we invite you to subscribe and stay up to date with the latest uploads on that channel. We'll also be posting this particular webinar up here in case you wanted to rewatch it or missed any portion of the presentation here today. We have a wide range of topics that are covered, including many other simulation videos, so definitely feel free to stop in and search the extensive archives on there. We also produce a blog on our website. It's very active. We have many tips and articles with useful information regarding SOLIDWORKS and many other technical topics, as well as fun projects that some of our engineers have been doing, things involving 3D printing and scanning as well. So definitely give that a look. All right, with that being said, we'll leave this webinar open for any other questions we didn't get to. If you're heading out, again, thank you for dropping by, and keep an eye out for our email newsletters for any new presentations or new uploads to our YouTube channel. All right, let's take a look at any questions you guys have here. Thanks for watching. If you enjoyed this webinar, please subscribe and leave us a comment below if you have a topic you'd like us to cover in a future video. Visit our website, goengineer.com, for access to professional training, upcoming events, and more from your #1 online technical resource. Bye for now. Take care.